going to be a conceptual or verbal review of thermodynamics and the thermodynamics unit of AP Physics 2. I'm going to talk about all the main topics conceptually, and then I'll make a video for math and a video for graphing. This is the verbal video. Thermodynamics is, I like to call it the study of energy. We're not really dealing with like kinetic or potential energy, but we are dealing with energy in the context of temperature and heat and like molecular energy and entropy. And I think thermodynamics really does deal a lot with energy. And the first kind of two vocab words that you learn in the unit, I already wrote it up because I was doing this video and I was super scatterbrained and was explaining it wrong. The first two vocab words are temperature and heat, and they're not the same thing. I used to think growing up that, hey, these were the same thing. It's like what's like two things that are the same thing? Like wait, well, like what's like I'm trying to think. What is like something? I don't know. I don't know what I'm trying to say. But I used to think that these were just two things that describe the same thing, but no, they mean different things. Temperature is really the average kinetic energy of like a bunch of molecules, right? So anything, right, that has temperature. So for example, like a burger or a bunch of gas or I don't know, someone with a fever, their temperature is really just the average kinetic energy of a bunch of molecules. And we use Kelvin for temperature, right? There's Fahrenheit, there's Celsius. Fahrenheit's, in my opinion, I like science, but Celsius is just stupid. I think Fahrenheit's a better way to measure temperature. That's a debate for another time. Kelvin is another way to do it, and Kelvin's nice because there's no negative Kelvin, right? The lowest possible measurement for, or I guess the lowest possible Kelvin you can get, lowest possible temperature is 0 Kelvin. What does 0 Kelvin mean? It means that your molecules are not moving at all. They have no kinetic energy. So the lowest you can go is 0. Heat, on the other hand, is its own form of energy, and it's specifically the transfer of thermal energy. So for that we use joules, right? Like it's joules, it's energy, it's the transfer of thermal energy. How does thermal energy transfer? Well, there's 3 ways it can transfer. It can transfer via my marker sucks. Oh my god. Conduction, convection, and radiation. Radiation. Hey, when you get a cup of coffee, sometimes they put a little spoon in it, right? If you think about a cup of coffee, there's a little mug, and I put a metal spoon in it. Why do they do that? Because I like to stir it. That's true, but there's also another reason. The what am I'm stuttering. Oh my god. The coffee, it's hot, and I want it, it's sometimes too hot and it burns my tongue. I don't want it to be too hot, so I put a spoon in there, and that heat transfers some of the heat. There's heat transferring onto the spoon, and that causes the mug to be at a lower temperature. The coffee is literally touching the spoon, and thus we get heating by conduction. The spoon, because of like direct contact, it starts heating up. I think conduction is as simple as touching something. If I touch something hot, wow, my hand burns because it is so it is so much hotter than me. It's at a higher temperature, so you get a flow of heat from. I should draw this out actually. So if this is something hot and I touch it, this, let's say, is, I don't know, 300 Kelvin, and my hand is at like 20 Kelvin. I don't know. because there's a temperature difference, there's going to be a flow of heat. We use the letter Q for that. A flow of heat to my hand, right, from the hot. Same thing with the cup of coffee, right? Hot coffee, there's heat transferring onto the spoon. Convection is really heating when you're dealing with like fluids and gases. Gases are fluids. I don't know why I said that. It's when you're dealing with fluids, right? If you have like a boiling water, right? Oh my gosh, this is like super dead. It's okay. I'll just roll with this. So, if you're heating something, yeah, it's gonna there's gonna be a fluid. Like if I'm boiling water, right? That's a fluid. So the bottom fluids heat up first, but then because they heat up, they become less dense, so they rise to the top, and then you get cold water sinking back down. So you get these kind of currents, convection currents, where it's flowing up, and then the hot water rises up, and that causes cold water to shift down. That's heating by convection. So that's how you could get that's kind of like how do I explain this? Like if you've ever initially if you have like wait I'm trying to think about what I'm trying to explain. There's so many times where I like I've had like something warmed up like tea, and then the hot is really warm, but then the bottom is really cold. So you kind of got to give it a mix so that everything kind of thermally equilibrates. It's that's kind of the idea of convection. Convection is really when you're dealing with fluids. All right, and the last thing is radiation. Radiation is a form of heat transfer without any kind of contact. The sun is really far away from us, and it's in space, and that's basically a vacuum, right? There's not a lot of molecules up in there. So how does that heat from the sun get to us? Well, it's by radiation through probably an electromagnetic wave. I don't know much about waves. But through a wave, it's able to get through space and radiate to us. So you don't need any medium, you don't need any fluid or contact. It just happens by distance, right? Like it radiates through it can radiate through nothingness basically. So radiation, the best example would be like the sun. So those are the three forms of heat transfer, right? 3 ways heat can transfer. Now, one thing you might have seen the stupid Kai Cenat. That's kind of mean calling it stupid. There was like a Kai Cenat stream where like Bill Nye was on it. Or you might have just done this in class. If you have something metal and you touch it, hey, that feels a lot cooler. And then if you have something that's like foam, that feels not as cool. It feels kind of warm. But then if you put ice cubes on both of them, the ice melts on the metal first. What's going on there? So hopefully it makes sense that when you put the ice cube on both of them, there's going to be some heat transfer by conduction, right? Heat will transfer by like touching. They're touching. So what's happening? I'm gonna use this marker. What's happening is if you have your 2 plates, I'm gonna say this is metal, this is foam, and then now my ice. The metal is more thermally conductive. What does that mean? It's able to conduct heat better. So with heating by conduction, because the metal is more thermally conductive, hey, you get not more heat flow, but your heat flows at a faster rate. And when I do my mathematical video, that hopefully will make more sense what I mean by when I say rate. But you get heat flowing faster with the metal versus the foam. So when you touch the metal, why did it feel so much colder? Well, they were both at the same temperature, but because the metal is so thermally conductive, it's able to take away your heat better. So when I'm touching the metal with my hand versus the foam, heat goes to the metal way faster than compared to the foam because the metal is more thermally conductive. So if you think about the coffee mug thing, why do I put a metal spoon in there? Well, if I put a wooden spoon or something that isn't as thermally conductive, the heat won't be able to transfer all the way to the the end of the spoon. And I should break this down on the molecular level of like what's going on with conduction, because temperature, average kinetic energy of a bunch of molecules. So if something's hot, its molecules are moving faster. When it touches something cold, those collisions. I think this is a good way to explain it. Like it's when you touch like a warm thing and a cold thing, the collisions in it's like the molecules are moving much faster, and that's colliding with the molecules in the cold item, and those molecules will on average start moving faster. As a result of those collisions, it starts getting warmer because remember, temperature increases when average kinetic energy of your molecules increase, so the whole thing starts warming up. Yeah, so that's the molecular level of conduction and convection. That was probably, wow, that was already, wow, how long have I been making this video for? 11 minutes on just this. Okay, we're gonna start going through these things a little bit more quickly. Okay, so, processes. If I have, this is probably something you saw a lot this unit, is, your confined chamber of gas and a piston. So this is my piston. We're going to talk about processes. Let's say we have a bunch of gas in this chamber. They all have instantaneous speeds v, or they're not all moving at the same speed v, but they're moving. That's what I was trying to say. They're all moving certain speeds. So, yeah, they're all moving. They all got temperature, right? Because temperature is the average kinetic energy. So this gas definitely has some temperature. What happens if we start moving this piston? What's going to happen? Well, if you have an ideal gas, which you can assume your gas is ideal, I need to still brush up on what an ideal gas means. I think ideal gas means I think all the collisions are elastic, and I have no idea. I'll learn what an ideal gas is. But you can assume your gas is ideal. It follows according to PV equals nRT. What in the world is PV and N and R and T? Well, first of all, P is pressure. So because of the collisions, right, these molecules, and this is KMT, but whatever, these molecules are moving around the gas particles, and they're going to start colliding with the wall and the piston, and those collisions create a pressure, and you can derive the equation using momentum and stuff. They're exerting pressure on the walls. So P stands for pressure in pascals. That's the unit. V is volume, so it's just your volume of gas. N is the number of moles of gas that you got. R is the gas constant, 8.31, and T is temperature. So, what happened? Well, there are three kinds of. There's more than this, but there's three simple ones that make the math easy. That three processes that could happen. Your pressure could stay the same, your volume could stay the same, or your temperature could stay the same. So for let's say for isobaric, that means your pressure is constant. So if your pressure is constant and I decrease the volume, my temperature decreases. So V is proportional to T. Let's try to make that make sense. If the pressure is the same, that means those collisions, the pressure caused by those collisions have to stay the same. Well, if I decrease the volume, if they're moving at the same speed, then there's less space and they're moving at the same speed. You can expect, yeah, there's going to be more collisions, right? If they're like, try to conceptually understand that. If I make the volumes less and they're moving at the same speed, there will be more pressure because they're moving at the same speed, but now they're more confined. But the pressure has to stay the same. So if I decrease the volume, they're going to move slower so that the temperature is the same. Or sorry, not the temperature, the pressure. They move slower so that the pressure is the same. And if they move slower, that means your temperature decreases. So if volume decreases, so does your temperature. And the other way goes too, right? Volume increases, they got to move faster so that you get the same pressure. Or I don't know, if you don't want to understand that, I mean, yeah, you could use the equation to figure that out. But that's why this is true. Like why this, I guess, proportionality works. Let's talk about now isometric. This means same volume. So now your P is proportional to T. Hopefully this kind of makes a lot of sense, right? If I'm keeping the same volume and there's more pressure being exerted, well, that just means that all the molecules are moving faster. So more temperature. Now, yeah, right? So if they're moving, they're moving faster, which means more temperature, and that means more pressure being exerted by those collisions. Hopefully that kind of makes sense. And then now there's isothermic. This means same temperature. So same temperature, that means now P, you would have to divide both sides by V, and you would see that pressure is proportional to the inverse of volume. So if you decrease your volume, you get an increase in pressure. Hopefully that kind of makes sense. Why? Same temperature means they're always going to be moving at the same speed no matter what. So if I decrease the volume, if they're moving at the same speed, they're more confined, so they're going to get more, there's going to be more pressure exerted. Same, otherwise, the opposite goes. If I make my volume bigger, they're not as confined, so there's going to be kind of less collisions, less pressure being exerted. Those are the three basic processes. I will, once I get into, like, the graphing and math, I'll talk about PV diagrams and stuff. But this is just to conceptually understand. Let's talk about KMT. I won't really write too much for KMT because honestly, KMT, it's kind of intuitive. Like, we're kind of using some KMT ideas here. KMT is kinetic molecular theory. It's a way to kind of help understand and model gases. If we think of gases as like these particles, and they're all moving around, and they all got their own momenta and kinetic energy. It's a way to just help model like what causes pressure. It's the collisions of those particles, right? If they're moving faster, you get more temperature, right? So more kinetic energy of each molecules means more overall temperature. And what KMT also helps us describe is if you had now two chambers, and they're both at 300 Kelvin, 300 Kelvin, but the molecules here are moving much faster, and then these ones are moving much slower. Well, hey, what has the heavier particles? Like which particles, like let's say they're like two different, like one is a heavier gas, like filled with heavier atoms or molecules, is lighter molecules. What would have the heavier element or heavier like molecules? Well, it would be the one with the slower moving particles, right? Because I know that their temperature is the same, so the average kinetic energy is the same. So if you think about K equals 1/2 mv squared, if the V is going down and K is constant, then M has to go up, right? There's more mass because they're moving slower, same kinetic energy. So KMT helps us kind of explain those kind of things. It also helps us explain like atmospheres, right? Escape speed. you could calculate escape speed by doing square root 2gm over, or 2g over 2, wait, is it 2gm over r? Yeah, 2gm over r, right? No, that's not right. I don't know, you could derive it, I kind of forgot. I think that's right. Yeah, that's right. Yeah, I don't know what I'm talking about. 2gm over r, square root that. Escape. That's how you get escape speed. So if your particles, right, and it's kind of this idea, if your atmosphere is at a certain temperature and you have a bunch of light molecules, well, they're going to be moving way faster, probably fast enough to escape and get out of the atmosphere because they're faster than the escape speed. But if your molecules are heavy, they're going to be able to stay in the atmosphere. They're not going to have enough kinetic energy to escape. Or no, that's they wouldn't, like, it's not kinetic energy, it's speed. So they'd be able to stay. They couldn't escape. So that's just a way to model gases. So hopefully that kind of makes sense. Let's talk about the first law of thermodynamics. The first law of thermodynamics is really a conservation of energy statement. So first law of thermodynamics. It says that so this really has to do with processes. Internal energy, right, is related to temperature, and its internal energy of a gas is really just the total kinetic energy of your particles, right? So the total, like if I were to sum up the total kinetic energy, that would be my internal energy. The change in internal energies, right? The change in the movement of these particles is going to equal whatever heat I put in and whatever work I do on the gas. So if I go back to the example of a piston, if, like, for an isobaric process, what's happening, if I were to, like, let's say, decrease the piston is exerting a force on the gas over a certain distance. It's doing work. So that work, we would say, is positive because it's work on the gas. It's adding energy to the system. So I would say that the work is positive. And then, well, what's happening to the temperature? Remember, U is proportional to T. So your internal energy is proportional to the temperature because both deal with kinetic energy. Because temperature is the average and then U is the total. So so if I decrease the volume, my temperature, it's going down, right? So that means less U. My change in U is negative. So in order to get an isobaric process, I need heat to flow out of the system. I need heat to be, or I need Q to be negative, right? I need heat to flow out of the system. The first law of thermodynamics helps me figure that out, right? For isothermic, my change in U is 0, right? There's no change in internal energy because the temperature remains constant. So if I decrease the volume, I'm doing work on the gas, and then, or let's say increase it. The gas, there's two ways to really think about this. The gas is doing work on the piston, so that's really negative work, right? If you think about, like, kind of conservation of energy, the piston probably will have some mass, so if the piston gets raised up, there's an increase in UG. Where did that increase in UG come from? It comes from, like, the molecules, like, they would have negative work done on them. That energy has to come from somewhere, so it's negative work, so that everything equates out. So if my work is negative because of the volume got bigger, hey, I need heat to be added in so that my change in U stays 0. So I can use first law of thermodynamics to kind of figure out what's happening to the heat and the work and the internal energy of my gas based off first law of thermodynamics. So yeah, that's first law of thermodynamics for you. It's pretty important. you know, it's a conservation of energy statement. I can't get a change in U unless I'm either adding heat or doing work, or removing heat, or doing negative work, or removing heat, or something like that, right? So, yeah, that's first law of thermodynamics. I have a sheet, by the way. This is why I'm always looking down there, because I made a sheet of all the topics I wanted to talk about. Let's think about engines now. Engines confuse me, honestly, they do. But that's okay. Hopefully me explaining it will clear up some of my own confusions. Here's how an engine works. An engine works by having a heat source, and an engine, and a heat sink, something that is cold. So, hey, when you have a heat source and something that's cold, what do you think is going to happen? There's going to be heat flowing down this way. So there's going to be Q in, right? Q, heat flowing into the engine, and then there's going to be heat flowing out of the engine into the cold part, the heat sink. Well, what the engine does is during that flow of energy, as Q is going in, it's taking that and it's going to do some work. Now, what do I mean by do some work? Well, if you think about a steam engine, right? The way a steam engine works is what Mr. Gustin showed us, is you have water and then you boil it into a gas. So there's heat going in and the gas is going to get really hot. So really the gas itself is kind of the heat source. So I really shouldn't say Q in. Like there's heat going in, but that heat is just making it into a gas. So gas, that's hot. It's going to start flowing in and it's going to start expanding into the piston, and then as it expands and flows into the piston, well, there's going to be heat that kind of goes to the cold parts, which is like the it's kind of like the what do I call it? Like the pipes, right? Like heat will be lost to the pipes, but the engine will still take some of that heat and turn it into work. So to think about conservation of energy, the Q that goes in equals the work plus the Q out, right? So if the Q in, right, if you think about like the heat from the gas, it's going to go into the piston. The piston is going to do some work from that heat, but also some heat will be lost to the cold surroundings of the engine. How neat would it be if you got no Q out, right? All the heat you put in would go into work. That's not going to happen. Unfortunately, I know. That's kind of a disappointment. Has to do, and I'll talk about it in literally like 5 minutes. That has to do with entropy, but it's really best explained with entropy. So I'll talk about that in a second. But hey, you could also have things that do the opposite. Let's say I want to get hey, this is kind of crazy. If we had something cold and we had something hot. Let's say I want to make this thing colder. What? You can't do that, right? Like this is hot and this is cold. If I want heat, can't flow the other way, right? Heat, like, and this is also another entropy idea, but things want to naturally equilibrate. So heat will not naturally flow from cold to hot and cause this hot thing to be hotter. No, heat will flow the other way. That's what naturally happens. But gosh darn it, right? Like I want to freeze water into an ice cube. How else am I going to do that, right? Well, if I want to do that, I need to actually put in my own work. And I put that work in to a heat pump, also known as a refrigerator, or something like, something, I don't know, whatever uses a heat pump. All it does is it causes heat to flow from the cold to the hot. And that's pretty nice because that helps me cool things down and freeze water and do all sorts of things. The main key idea, and I'll draw an arrow to make sure I know which equations which. The main key idea is that I need to put in work to get heat to flow the other way so that I can cool things down even colder. So yeah. That's there. There you go, right? Your engine and your refrigerator. Now let's talk about entropy, because oh man, entropy. There's a whole video called "The Most Misunderstood Concept in Physics," and it's literally about entropy. So entropy, when you're thinking about energy and you're thinking about molecules and their movement, entropy describes how random, how disorganized, how dispersed that energy and movement is, right? So I'll say, measure of disorder, I guess. This is a cool idea. Let's say I had a car and I could break it to produce, heat, by friction, right? To produce some heat energy by the friction between the tires and the thing. And hey, maybe I could channel that heat to cause the car to move again, right? I could channel that heat. Conservation of energy applies there, right? Heat energy equals K. I can use that heat energy to keep my car moving. Why wouldn't that happen? Well, if you think about it, if I break my car, right? If I why am I saying break my car? If I slam the brakes on my car, the tires will rub against the road, and the road gets hotter because its molecules will on average start moving faster. The motion gets more the molecules and the movement of the atoms gets more disordered and random. Why can't I use that energy to go faster? Spontaneously, I can't make the atoms. First of all, right? If I want to get from heat energy to K, I can't make the heat. I can't make the atoms start slowing down to get more organized, and then that organization will get the car to start moving, right? Because that loss of heat, how do I transform the heat to kinetic energy? Well, then the heat would have to go away, but how do I do that? Yeah, the atoms and the molecules will have to start moving slower again, but that won't happen spontaneously. That's actually the second law of thermodynamics. The second law of thermodynamics says, and I'll just write it this way because this is just easy to write. Entropy tends to a maximum. What that means is that entropy will naturally increase or get bigger. I will never have a spontaneous decrease in entropy. That actually explains why heat flows from hot to cold. If I have something hot and something that is cold, the energy, there's low entropy because all my energy is more organized into the hot part. And second law of thermodynamics tells us that energy will naturally want to get dispersed, become more random. So if my energy wants to get more dispersed, more random, then I'm blanking here. If my energy wants to get more dispersed and random, heat will flow to the cold so that the energy is more dispersed, more random, more disorganized. But if heat flowed from cold to hot, then what you would see energy becoming more organized, becoming more sectioned, more compact, more organized. Yeah, I think I said that already, but yeah, more organized. But why can cold flow to why can heat flow from cold to hot? I gotta put in work. So if I put in work, I can get a decrease of entropy. I just need to put in work for that to happen. It won't happen spontaneously. Entropy leads us to this idea of reversible and irreversible processes. So a reversible process is really just one where the total entropy stays the same. If I think about an isobaric or isothermic, or sorry, isobaric or isometric, like if I think about an isobaric, in like if I increase the volume, how do I do this? Yeah, okay, if I decrease the volume, I know that heat will flow out of the thing I talked about, the first law of thermodynamics. So I know heat will flow out. If heat flows out, that means entropy is increasing, right? Because the energy is getting more dispersed, more random. So the reverse will not happen. Entropy will not naturally decrease. So the reverse will not happen. That's an irreversible process, because if the reverse did happen, I think the entropy would increase. Now, what if the entropy stayed the same? Well, then you could have a reversible process, right? Because if entropy stayed the same, the reverse could happen. When the only reversible process of these three would be isothermic, because it remains at the same temperature. So if you don't have a temperature difference, like between the surroundings and the gas, then the reverse, like heat could flow one way or the other, because they're at the same temperature. So that would be a reversible process, and that's one where the entropy stays the same. Naturally, like it could go one way or the other. So that's second law of thermodynamics and entropy. There's this guy called Carnot, and he knows. See what I did? See what I did there? Carnot knows. He thought of the most ideal engine possible. It's really one where you have a heat source, and that would get into an engine, and then you would have heat flowing into your the cold again. But hey, what if the work that goes out of it goes into a heat pump, which brings heat from the cold back to the hot, and then you could connect them and have it kind of be like a cycle where hot flows to cold, and then that same work will get the heat from cold back to hot, and it would kind of be like a perpetual motion machine. Highly theoretical, and it wouldn't even really be that useful, right? Because then all the work would have to go into the engine. As soon as I try to use some of that work to power my bike or something, then this wouldn't work. All the work would have to go in back to all the work would have to go into the heat pump to get. So this would be an engine, and then the work outputted would go into the pump to get heat to flow back. So this is the idea of a Carnot process. It's a cool idea, but it's highly theoretical. This wouldn't happen in the real world, because first of all, you have losses to the environment, but also because you couldn't use the work for anything. So it's not really all that it's cool, but it's not like this could solve our energy crisis or anything. So this is known as the Carnot process. The way an actual Carnot cycle works is essentially you have a hot reservoir, and that would expand. So if you had your piston gas situation, if you had a hot reservoir underneath this thing, it would expand isothermically, because heat is entering into the gas, but then the piston also expands. So heat would be flowing in, but your work is negative because the thing is expanding, so your change in U stays the same. That's an isothermic process. But then what happens, you take away the heat reservoir, and you will get a ambiatic, I forgot what it's called, I think it's ambiatic, I think. You get an ambiatic process, which just means that no heat is flowing. So as the piston keeps moving up, when you take away the heat reservoir, right, it's moving up, but it's gonna, that work is still negative, right, because it's still moving up, and the gas is doing work on the the piston. So work is negative. There's no heat flowing in or flowing out because that's an amniotic process. So the change in U is also negative. So the molecules are going to cool down to that of, the molecules will cool down to the temperature of your cold bar, and then you put in your cold bar, and you get another isothermic process, right, where heat would flow out of the gas into the cold bar, but your piston is doing positive work. So negative, positive, you get zero change in U, so that's an isothermic process, and then you can get another ambiotic process going by taking out the cold bar, and then it would keep compressing, but then it gets hotter, and then once it gets because it's an ambiotic, right? So then work is positive, change in U is positive. So then as your thing gets hotter, you would then put in back the hot bar, and then you would see heat flowing in, boom bada bing, boom bada bing. You got a Carnot cycle. So yeah, this would be the most ideal engine ever. Probably not useful, but yeah, so this is kind of thermodynamics. Hopefully this video helped you conceptualize some things. I don't know, prepare for the test. Hopefully this was helpful in some way. Yeah, thank you for watching this. Let's see how long. 41-minute video. Wow.